Okay, let's now talk about second order or higher order derivatives. So, what do we mean by that? Well, let's say I've got a curve that looks like this. Okay? Just a nice, weird looking, kind of exponentially curve. Now, the idea is, as this function changes, the gradient also changes, right? So let's say my gradient here is, well, that looks kind of like a straight line. So let's do my gradient here is minus 10. Okay? So my gradient here is minus 10. And then my gradient here is minus 5. Then my gradient here is minus 2. My gradient here is minus 1. And then it minus 0.5 and minus 0.25. And it slowly gets closer and closer to a gradient of 0. Well, not only is my function changing, but my gradient is also gradually changing. And when something changes, we can differentiate it. And because gradient changes, that means we can differentiate gradient. But gradient is already something that's been differentiated. So it's a bit weird, but we can keep differentiating something basically as long as the function will allow us to. So if I had, say, y equals x cubed plus x squared, I can differentiate that once to y dx to find how the function changes over time, or or what the gradient is, 3x squared plus 2x. But then I might want to know, well, how does that gradient change? So in this example, how quickly does the gradient go from minus 10 to minus 2? And if I want to find that, well, I need to differentiate it again. And the way that I write that is d2y, it looks like it says d squared y, but we generally say d2y over dx squared, which we don't say is dx2. They're both squared, but the top one we don't say is a squared. Don't ask me why. d2y over dx squared. And we just differentiate it again. 3x squared becomes 6x, and 2x becomes 2. And now I've got how much my gradient changes by. It's the gradient of my gradient. So can I do it again? Yeah, of course I can. I can then do a d3y over dx cubed, which will be 6. And then technically I could do it again, d4y, dx to the 4, which would just be 0, because I haven't got any x's left. And then anything after that would just be 0. But technically, I can keep differentiating something for as long as there are x's still present. So here I've got the gradient, here I've got the gradient of the gradient, here I've got the gradient of the gradient of the gradient, and here I've got the gradient of the gradient of the gradient of the gradient. And you're probably like, well, this is a load of rubbish. He's a nutcase. Why would you want to do this? This is ridiculous. Well, actually, this is one of the most common things that we do in physics, especially, and a bit of maths as well. The reason for that is in mechanics, or if you like, just in everyday life of things moving, everything has a position, right? A set of coordinates, how far away something is. It has a position. And let's say my position is y. If I differentiate this, so I go to dy dx, then I end up with my velocity. And I'll probably end up making some mechanics videos one day that explain this in more detail. But if I take something's position and I differentiate it, I find out how fast it's going. And then if I differentiate it again, d2y over dx squared, I find out its acceleration. So these are very important things that I need. And just by finding the second derivative, I can get my acceleration. And in fact, it keeps going. If I differentiate this again, I get something called jerk. And then if I differentiate it again, and I get d4y by dx to the 4, I get something called snap. And then if I differentiate that again, I get something called crackle. And if I differentiate that again, I get something called pop, which I hope is the title of this video. And yeah, you probably haven't heard past acceleration. And to be honest, as someone with a physics degree, I don't think I've technically ever heard of anything past acceleration either in an actual application case. But the point is, if you keep differentiating things, we've named them, so they must be important. And we've named them after cereal, so, you know, they really must be important. Point being, at least up until the second derivative, things are very, very useful. And when we get onto differential equations in 112 episodes time, you'll see that a second order derivative is very, very useful in real life, not only with acceleration, but other things as well.